Hey, so our next presenter is Boris Daszuta from the University of Otago. Are you a student or a lecturer or? Cool. Postgrad? Brilliant. Cool. And Boris is here to talk to us about that stuff, which is probably the most fantastic title. I'll do it. A Path to Multi-Arbitrary Precision Distributed Computation with Python3. Thank you very much, Boris.
Yeah, so I'm here to talk about a package that I've been developing in order to facilitate solution of some nonlinear PDEs associated with the problem in my thesis. So let me start saying things. So first, I just give a little bit of background. I mean, I'm assuming that if you're here, you're probably familiar with things like NumPy, SciPy, and so forth. And you've probably heard of something like mpmath and SymPy, which gives you an extension in precision, and it also has a lot of the kinds of algorithms that are within NumPy. And then I will sort of give some prototypes to describe or to fix a nice problem that we can attack. And then I'm going to go and look at the internals and so forth, and yeah, we'll get there. Okay, so you've probably encountered this, that, oh, hey, Python is a fantastic glue language. Ah, yes, but this is a little bit unfair because we can do even more. We can write nice Python code and that can be made to match C execution rates. So this is this idea of just-in-time compilation. So there's this nice library, I don't know if you've heard of this, but this is called Number. I'll say a little bit more following this. Yeah, so we have this very rich kind of numerical ecosystem that we want to leverage to solve problems quickly. But we can actually also make use of another nice new package. I think this was actually developed mostly this year. So there's this thing called Dask. Now, this gives you the possibility for doing out-of-core calculations and parallel calculations. And if you use the right kind of scheduler, then you can do distributed calculations. And it's all basically the same piece of code. So this is good. Makes things easy for us. Okay, so again, as I say, we want to solve some partial differential equations. And the particular methods that I'm interested in are spectral methods. So these are extremely high-order methods. But there is a bit of a downside because they usually lead to ill-conditioned systems. So hence why I would like to do some arbitrary precision stuff. Okay, so first thing, I will just give you a very, very simple example of what a number is. So you can imagine writing some kind of horrendous thing like this that would probably be quite slow to execute. But you can essentially, for very, very minimal effort, insert this kind of decorator. And this will generate some compiled code. But yeah, it's very, very simple. And there are some kinds of nice things that you can also do. So if you pass these things like no-gil, then you can avoid global interpreter lock, which is nice because then you can also do threading very, very easily. Yeah. I'd like to point out and make some more comments about Dask because I think this is fantastic. So let's consider constructing some array with elements that are like this. Schematically, you'd write something like this. So notice that this looks very much like just NumPy stuff, but you're inserting this chunks parameter. So in contrast, what happens when you use Dask is that you have this directed acyclic graph representation of the array. So it's not immediately constructed. You have sort of some nested dictionary of dictionaries that tells you how this will be constructed. So yeah, you can then pass this to a scheduler and you can execute it. And yeah, you can fiddle with chunks if you want to do this in a distributed fashion. Right, so let's make some kind of modest goal. So let's say that we'd like to write some algorithm representing some mathematical problem. We'd like to only write this once. And in particular, we'd like to be able to sort of leverage mpmath and SymPy, and we'd like to be able to do this in a simple way. Okay, we will introduce this notion of specifying an evaluation library. So I construct this kind of class that has these Lib-if evaluation library type things. And the idea is that, well, you can subclass NumPy arrays and you can have bound attributes that have this information stored within it. Now, why can you do this? Well, usually you think of a NumPy array as containing some kind of float data, but you can also stick object types in there. So you can leverage all the kinds of underlying algebraic structures and so forth that already exist in NumPy arrays. Okay, so what else would we like to do? Well, we'd like to have this kind of function delegator construct, and with it we'd like to have bound methods that are pretty much the same kind of syntax as NumPy, but now we can pass this additional parameter, Lib-if. So here this LM represents an evaluation with mpmath at a precision of, I think this was 30, yeah, 30. And ls would be evaluation with SymPy. So you'll notice, for instance, here I pass Python3 to sign, and the exact result, very, very accurate result, and then float result. We'd also like to be able to do something else. So if you noticed when I actually gave this number slide, I very, very awkwardly defined some functions. Now, the reason I did this is because, okay, if we have these delegated functions and we can pass to them a parameter that allows us to return a function handle. So, sorry, this is getting a little bit convoluted now. But if we have this ability to return sort of the native NumPy functions, then we can still use the same piece of code and have this compilation and still avoid GIL using this no-GIL parameter. Okay, so let's make a prototype problem and see how this would all work. So here I'm just defining matrix elements in this way. So if you like, this is a representation of a Hilbert matrix. And these things are horrible because they have an enormous condition number. So roughly, whenever you try to increase, or whenever you try to solve a problem and you increase the condition number by power of 10, then you will lose an order of precision in your result. So here we are going to, because this is a symmetric matrix, we're going to attack this with a Cholesky decomposition. So okay, you'd like to write a piece of code like this. So here you make a context with mpmath evaluation library, and here I'm just increasing the dimension of this matrix. So yeah, I have embedded a prototype representing this Hilbert matrix, and I pass this to this Cholesky solver, and then I make use of sort of standard syntax. Okay, but what if this in was actually enormous, or this calculation was slow? Well, we'd like to go back and use Dask. So what we'd like to do is, well, we'd like to have consistent interfaces such that we had this previous code here, and we would just replace these functions with the equivalent delegated Dask functions. But we'd have to specify just an additional chunks parameter. So, okay, we'd like to do this, and we can do this. And this appears to actually work quite nicely. So if you look at this red line, this is the error if you do this computation with NumPy at float 64. And if you look at the blue and green curves, then these are mpmath equivalents. I also do this computation with this Dask implementation, just to compare sort of whether this is consistent. Okay, so what's going on? How is this working? Okay, so if we look at this Lib-if object, then this must have to it bound some methods and some information. So for instance, is a particular type that you're specifying a native number type that can be compiled with this no Python and no GIL parameter, or is it not? So for instance, in the case of complex 128, it is. In the case of something like a SymPy rational type, then it's not. And then we have various methods that allow us to extract the actual class directly. And we have methods that stipulate the representation of the type as it would appear in a NumPy array. Okay, so how do we specify just a number? Well, we'd like to delegate this based on some input. So we'd either like to just, if it's for instance a float and we require a float 64, just store it. If we pass a string like this fraction and we'd like to represent this as an mpmath, then we'd like to pass that input to mpmath.mpf, which allows for the construction of this thing. So we have to do this kind of business here. What is nice is that you can actually subclass this in NumPy in array, and you can provide, well, you can have it carry this Lib-if data, but you can also do some further trickery. So you can provide hashing capability for this, and this allows you to cache things and speed up calculations at key points. You have to be very, very careful when you do this, because this should only be done for immutable types, but hey. Okay, so how are we actually pushing given some Lib-if to the correct function? Well, here I just give a very, very short snippet based on some already implemented functions. So if you look at this mpmath, well, this should be just a dictionary of key equal to value, because you want your API to essentially mirror that of what is in NumPy. The annoying thing is that different numerical libraries will have different names associated to the same kind of mathematical function, so you have to start playing these kinds of games. Now, a further thing that you'd like to do is you'd also like to have NumPy type broadcasting for whatever function you're calling. So this is why I have these kinds of bracket things. So you leverage this numpy.fromPyfunc. And the idea is that you're writing a script that is what you can think of as some kind of function constructor. So based on some Lib-if input, it will push you to the correct numerical implementation. What else would I have to say? Sorry, I can't actually see these things here, so I have to, I have to do this. Okay, and in the end, what you'd like to do is you'd like to inject this into a single class so you can conveniently access every single function that you either implemented or you pulled from some numerical library and so on. So, okay, if we followed that approach and had a lot of coffee, then we could actually do this for pretty much whatever kind of function. So here I have some, or a lot of the NumPy functions that can be evaluated with whatever kind of Lib-if you care about, and then I have some additional things which make use of this just-in-time compilation, which in this case are some linear algebraic things and some polynomial, and some things associated with polynomial families. Here's some call graphs. So in this case, I compute, I just evaluate or specify this 1/2 using this mpmath library approach. What is not shown at the end of this thing is that you're calling mpmath.mpf. And on that side, you would have mpmath.sign. So if the particular function is implemented in that library, then this is what this looks like. If the particular function is not implemented in that library, or you write your own implementation, then you'd have something more like the right, where, okay, your function constructor has to go away and look at the actual definition that you've provided and then does all the evaluations from there. On the left, you're just pulling np.arange. Okay, so that's kind of great. We can do this local function delegator or dispatcher business. So how do we actually get this to work with something like Dask? Well, you have to be sneaky, and this is this is very hacky. So what you're actually doing is, when you do this distributed thing, you spawn a whole bunch of different Python processes. And okay, let's pretend these are locally. So we've locally spawned a whole bunch of different Python processes. What we do is we have Dask instantiate these function delegators, and then instead of using the native implementations within Dask, you map element-wise to elements which are bound within these function delegators, which you've instantiated on each of these processes. So this is pretty horrible, but it can be done and it does work, and I don't claim that that's the best way to do it, but right. And then, well, we'd also like to do some simplifications in other ways. So we'd like to be able to specify functions in the following kind of approach. So you have a particular function, and to it you think of having some associated variable labels. And what you'd like to do is you'd like to be able to do some symbolics directly in your Python interpreter. So here what I'm doing is I'm constructing some function containers, and I'm saying that we have our function if, which is a function of x, y, n, and then what happens is that this becomes alphabetically reordered such that you have f of n, x, y. And the reason for this is that when you want to start having a composition of functions, so for instance, here, you need this canonicalization such that this evaluation works consistently. And if you wanted to, well, you could think of component containers where you have functions with indices that represent something like a tensor, something like that. Here, well, we'd like to continue this kind of abstract approach. So we'd like to have grid mappings embedded. So usually when you formulate some kind of PDE problem, you have this with respect to some geometry, say, and the actual numerical method that you're wanting to use is formulated with respect to some fundamental grid, which is different to this geometry. And what invariably ends up happening is that you have to map a whole bunch of differential operators, and you have to do a lot of work by hand to rewrite the system into this kind of adapted grid. But why would you want to do that when you could write some operators that do this for you? So here I'm just doing a grid mapping from the unit square to some square with side length a2 minus a1, b2 minus b1. Okay, you can also take these function containers and great, you have all this capability to do symbolic manipulations, but you also want to be able to evaluate these things numerically. So here, I don't want to get into details, but essentially you can construct grid objects and then feed these to these function containers, and then you still have all the nice algebra associated with that. And yeah, okay, here I'm getting a little bit carried away, but the point to draw here is that I wish to introduce now these quadrature and derivative operators, which represent taking derivative analytically and integrating analytically. So, yep, let's continue. Okay, so now let's change track a little bit. I'd like to describe this pseudo-spectral approach for solving PDEs. So this may look a little bit complicated, but the essential idea is that you have some function and you expand this function in terms of a basis. So you have this weighted sum where these phi in are your basis functions. And well, why do you care about doing this pseudo-spectral thing? Well, you have this extremely rapid convergence property. So if you look at the magnitude of a coefficient that multiplies these basis functions, well, this should decay very, very rapidly as you increase this little n. And yeah, so where do these phi in come from? Well, these are just some well-known classical polynomial families. Okay, so let's use that. Let's do some sanity checks. So supposing we took these polynomial families and we looked at those which are defined with respect to bounded domains. Well, we'd like to check that we can integrate these and we can differentiate these and so on numerically. And again, we do this by introducing some new kind of test polynomial. Here I'm just arbitrarily setting fn to be this combination and gn to be that combination. And this horrendous looking thing, it's essentially just taking a polynomial, differentiating it, multiplying it by the other, or differentiating it twice. And the point is that this row x is of fixed order. So the power, if you multiplied all this out, the highest power of x would be some fixed number. And we know that if this is this fixed number is 2 times capital N, then any scheme that we construct will be exact. So then I introduce this sum here. All this is a representation of this row being integrated. And you integrate it with a bunch of different schemes. So this capital X represents different lattice choices, so how you sample these polynomials. And you can do a similar thing with unbounded domains. The details here are not so important. I mean, I just want to check that the numerical schemes actually make sense. So if or are implemented correctly. If we look at that and we take the usual Chebyshev polynomials as basis functions, Legendre polynomials, and for instance, Jacobi polynomials, then we find that we can evaluate things and we lose precision as we increase this capital N. However, we are working consistently because our errors when we look at this strange epsilon function that I introduced are sort of reasonable. And if we increase the precision with which we do the computation, then okay, we can just keep going. Similarly, on unbounded domains, if we look at the derivative errors, we get something that is reasonable. So here you're looking at Hermite polynomials and Laguerre polynomials. There you're looking at Hermite functions and Laguerre functions. So this is why, because these are polynomials and because you're working on unbounded domains, you're always going to have this kind of error growth. But you can still decrease this as you wish. Okay, so let's introduce some test PDE problem. So here I just take a Dirichlet-Helmholtz equation in 1D for simplicity, and I impose the boundary condition that this thing dies at the edges of the numerical domain. So we take Legendre polynomials, or we take some linear combination of these things, which satisfy these boundary conditions, and we can substitute these things in and integrate against our test function phi, and essentially end up with a linear system. So this thing here. And this turns out to be ill-conditioned, because this is a sort of characteristic thing of these pseudo-spectral approaches. So, okay, we do a self-consistent convergence test. So how does this work? Well, you look at this original PDE and you say, okay, well, maybe I don't know how to solve that, but I could manufacture a numerical solution by sneakily first specifying a psi, plugging it into my equation. If you do that, you will then have a right-hand side f, and you take that as fixed by this analytically specified psi, and then you go back and you try to numerically reconstruct what you originally fixed. If you do that and you compare errors, then you find that, okay, this you can control. And this is actually quite nice, because if you look at the decay, or the tails, these are linear on this semi-log plot, so you have this exponential convergence. And you can avoid a lot of issues. And this is for taking some kind of Gaussian wave packet, so the actual data that you first fix in order to construct this right-hand side inhomogeneity is actually non-trivial, so yeah. Okay, so what would we like to do now? Where do we go from here? Well, I guess we have shown that you can reasonably do these kinds of things. But the point is that you'd like to actually have all this abstract operator stuff sort of working well, and at the moment I'm still trying to, yeah. And another idea is that, okay, there's this mpmath package is written by this Johansson person, but he's also written something called arb, which is a native C implementation of this. And it turns out that someone in Julia land has written bindings to these, which is quite nice, because if you have a numerical package written in C that works at arbitrary precision and is rigorous, well, it's quite fast. So, yeah, we don't appear to have Python3 bindings for that, and it would be useful to have them. But, yeah. Okay. I guess, questions? Thank you for listening, this kind of thing.
Thank you, Boris.
Yeah.
So we're going to be handing out the test papers now. This is worth 15% of your final grade for the semester.
Yeah, I'm sorry that I kind of, yeah.
So I hope you got all of that. Yeah, we've got plenty of time for questions. So anybody wanna throw something out there? Cool, Tim.
I got a bit carried away, I guess.
Just a real basic question. How many digits precision have you needed to go to for some of your work?
Well, okay, the actual problem that I'm wanting to solve I did not describe at all, but I've had issues. It's complicated. I've had issues. Well, okay, let's back up. I guess I have a little bit of time, so I can talk about that.
Wait, I have a question.
Yeah.
What is the actual problem you're trying to solve?
So the idea is that you want to construct initial data for simulations in numerical relativity. And to do this, you have to solve constraint equations. And to do that, we're using a funny kind of setup where you do a kind of deformation of solutions. So you take some nonlinear system and you linearize this thing, and at each step you're solving a linear problem and then iterating this. And this is where the issue is. Because this is ill-conditioned, you can't get a solution to the full nonlinear thing that is sufficiently accurate if you take a sufficiently high band limit. So a sufficiently large n when I was doing these plots. So that's the kind of frustrating thing, which this should address. And in principle, if you evaluate that with something like 20, 30 dp, in the end you'll get something that looks to be accurate to what you'd usually expect at float, kind of, yeah.
Anyone else? Cool. Okay. Thank you again, Boris. That was heavy. That was awesome. Thank you very much.
Sorry again.